Next, we look at the preparation of insoluble salts. We look at the precipitation reactions. Now, let's say you have been given two salts, sodium iodide and silver nitrate. Both of these salts are soluble in water. That means when water is added, they form clear and colorless solutions. So we are starting with two soluble salts in their solutions. When we mix the two solutions, a bright yellow color appears. This is actually a precipitate, which is an insoluble solid formed from combining two solutions. This is known as the precipitation method. Sodium iodide and silver nitrate have undergone a double displacement reaction, whereby the silver and sodium ions have switched places, creating silver iodide and sodium nitrate. Since sodium iodide and silver nitrate are soluble in water, they form aqueous solutions. We know that sodium nitrate and silver iodide are formed, but how do we know which is the precipitate? We simply refer to the solubility rules. All nitrates are soluble in water. Iodide salts are soluble except when combined with mercury, lead, and silver. Therefore, silver iodide is insoluble in water, and that is the bright yellow precipitate formed. So, sodium nitrate is an aqueous solution, and silver iodide is a solid precipitate. To isolate the silver iodide salt, we filter it through a funnel lined with a filter paper. We can also rinse it with distilled water since it's insoluble. The solid collected is known as the residue, and the liquid is called the filtrate. Now, can you predict the products for the double displacement reaction between barium chloride and potassium sulfate? Remember, the state symbols are very important. Here is the equation. It appears balanced. Using the solubility rules, we see that all chlorides are soluble except those of silver, mercury, and lead. So, potassium chloride is soluble, forming an aqueous solution. Almost all sulfates are soluble except a few, one of them being the barium sulfate. So the complete equation is as shown here. Next, we move to complex ions. Now, let us study the effect of adding sodium hydroxide and ammonia solution to a salt solution. We start with a solution containing calcium ions in a test tube. We add a small amount of sodium hydroxide solution. A white precipitate is formed. Then we add excess sodium hydroxide, and the white precipitate persists. Next, we have a solution containing lead-2 ions. We add a small amount of sodium hydroxide. A white precipitate is formed. We proceed and add excess sodium hydroxide, and the white precipitate dissolves. Next is a solution containing zinc ions. We add a small amount of sodium hydroxide. A white precipitate is formed. Then we add excess sodium hydroxide, and the precipitate dissolves to form a colorless solution. And now a solution of iron 2 ions. We add a small amount of sodium hydroxide. A green precipitate is formed. The precipitate does not dissolve even in excess sodium hydroxide. Next is a solution containing iron 3 ions. We start with a small amount of sodium hydroxide. A red-brown precipitate is formed, and even in excess, the precipitate persists. Finally, copper 2 ions. We add quite an amount of sodium hydroxide, and a light blue precipitate is formed. And so in general, sodium hydroxide forms insoluble hydroxides with the ions of calcium, magnesium, zinc, aluminium, copper. The hydroxides of zinc, aluminium and lead react with excess sodium hydroxide to form soluble complex ions. The same results would be obtained if we used potassium hydroxide. Now we repeat the same procedure using ammonia solution, which is basically ammonium hydroxide. We start with a solution containing calcium ions. We add a small amount of ammonium hydroxide. A white precipitate is formed. In excess ammonia solution, the white precipitate persists. Next is lead 2 ions. Add a small amount of ammonia solution. White precipitate is formed. Excess amount of ammonia solution. The white precipitate persists this time. Next is zinc ions. Small amount of ammonia solution. A white precipitate is formed. We add excess amount of ammonia solution, and the white precipitate dissolves, forming a colorless solution. Then iron 2 ions. Small amount of ammonia solution. A green precipitate forms that persists even in excess ammonia solution. Next is iron 3 ions. When ammonia solution is added, a red-brown precipitate forms that persists even in excess ammonia solution. Finally, copper 2 ions. We add a small amount of ammonia solution, and a light blue precipitate is formed. When we add excess ammonia solution, the precipitate dissolves to form a deep blue solution. And so in general, ammonium hydroxide or ammonia solution forms insoluble hydroxides with the ions of calcium, magnesium, zinc, copper, lead, iron, and aluminium. However, the hydroxides of zinc and copper dissolve in excess ammonia solution due to formation of complex ions. Next, we look at solubility and solubility curves. Now, we talked about soluble and insoluble salts. For the salts that are soluble, some of them are more soluble than others at a given temperature. If we were to compare copper-2 sulfate and potassium sulfate, we find that one is light blue and the other is white. If we try to dissolve them in water at equal temperature, we find that copper-2 sulfate is a lot more soluble than potassium sulfate. In other words, copper-2 sulfate has a higher solubility in water. This is actually a physical property of a substance, much like the substance's melting points and boiling points. The solubility of a salt is usually measured in grams of salt per 100 grams of water. So, would you think solubility increases or decreases with temperature? The answer is that solubility usually increases with increasing temperature. So, if we dissolved copper-2 sulfate and potassium sulfate in hotter water, we will find that more of each salt is able to dissolve. This observation is only applicable to solids dissolving in liquids. We can measure how much of a given salt can dissolve in 100 grams of water at a certain temperature. Then we plot solubility as a function of temperature to give a solubility curve. Here are solubility curves for copper-2 sulfate and potassium sulfate. We can see that for all temperatures, copper-2 sulfate is more soluble than potassium sulfate. From the solubility curve, it is also possible to find the solubility at a certain temperature. Let's say we wanted to find the solubility of copper-2 sulfate at 90 degrees Celsius. We take a ruler and draw a vertical line starting at the x-axis at 90 degrees Celsius until it reaches the curve. Then we draw a horizontal line from the point on the curve until it reaches the y-axis. At 90 degrees Celsius, approximately 68 grams of copper-2 sulfate is soluble in 100 grams of water. To compare, at the same temperature, only 24 grams of potassium sulfate would dissolve in 100 grams of water. Using the same graph, try and find the solubility of potassium sulfate at 60 degrees Celsius. The answer is around 18 grams of potassium sulfate per 100 grams of water. When a maximum amount of a certain salt is fully dissolved at a given temperature, the resulting solution is said to be saturated. In a saturated solution, no more salt is able to dissolve. If you took the saturated solution and allow it to cool, it will become a supersaturated solution. This means there is more salt than is able to dissolve at that temperature. When this happens, some of the salt may crystallize or come out of solution. This is called crystallization. Finally, water hardness. Now, if you wash with soap using rainwater, washing is easy and there's plenty of bubbles. We say the water is soft. But if you used well or tap water, sometimes it's difficult to get lather and scum forms. In this case, we say the water is hard. Water hardness is usually caused by presence of calcium ions dissolved in water. Water coming from rivers or wells has had to flow through rocks, and if they contain soluble calcium ions, the water will become hard. All the salts dissolved from rocks end up in water bodies, but when water evaporates, thus forming rain, the salts are left behind, meaning the rainwater is always free of salts and therefore soft. However, gases from the air can dissolve in rainwater. One of these is carbon dioxide. When rainwater falls on limestone, that is calcium carbonate, the limestone dissolves slowly, forming soluble calcium hydrogen carbonate. This form of hardness is called temporary hardness because boiling reverses the process and the hardness is removed. But the limestone will deposit in pipes and utensils, forming something called a limescale. Another form of hardness is called permanent hardness, which comes from rocks containing gypsum, which is calcium sulfate. In this case, you do not get limescale, but you get a scum. So, what is this scum? Soap is made by boiling natural fats and oils with sodium hydroxide. The soap molecules, for example sodium stearate, have a long tail which is attracted to the oil or dirt, and a sodium ion head which is attracted to water. In this way, dirt is lifted off your hands and clothes and is carried away by the water. However, calcium stearate is insoluble. So if the water contains calcium, the soap will not work until all the calcium ions have been precipitated out as scum. Detergents are sodium salts of compounds called alkyl benzene sulfonates, whose calcium salts are soluble, and so there is no formation of scums with detergents. Removing hardness in water. Let us start with the soap molecule, which is sodium stearate. We've said that it is difficult to use soap or sodium stearate with hard water because it will form a scum. If you keep using the soap, the water will eventually soften as the soap reacts with all calcium ions, forming a scum which flows to the surface as a solid. And once all the calcium is precipitated, the soap works normally and you get lather again. However, this wastes soap and the scum can stain brightly colored clothes. So we need something that will react with the calcium ions in water and form a precipitate. One such is washing soda, sodium carbonate. Once added, the calcium ions join with the carbonate ions, forming calcium carbonate as a precipitate, leaving water free of all the hardening ions. Only the sodium ions remain in the solution, balancing the sulfate ions and hydrogen carbonate ions, which used to be with the calcium ions. Temporary hardness can be removed by boiling the water, as we saw earlier. But this is expensive and causes calcium carbonate to deposit on your utensils. Boiling decomposes calcium hydrogen carbonate into calcium carbonate, carbon dioxide, and water. The best way to remove hardness is to use something called an ion exchange resin. These have fixed anionic lattice, a lot like clay, initially balanced by sodium ions. As hard water flows through, the calcium ions are exchanged for the sodium ions so that the calcium ions stick to the clay and the sodium ions come out into the water. In this way, the water is softened. Obviously, after some time, the resin gets full of calcium ions and has to be reactivated. And to do that, we pour concentrated sodium chloride. Very high concentration so that it's high enough to reverse the reaction, and calcium chloride comes out in solution. And the column is again full of sodium ions and ready for use.